Hello everyone, welcome back to the video. So today we're going to be looking at how does a calorimeter function. Your do now is to clear your desk of everything except for something to write with, a reference table and your iPad because you were taking the quiz. Anyone who hasn't taken the quiz, just let me know and I will give you a new version of it. Your homework is this matter and energy packet page. All I really want you to do on it is tell me whether the thing listed is a physical change or a chemical change. So, before we begin, let's talk about servings. How many calories are in your favorite snack? My particular favorite snack is 230 calories. Well, to be honest with you, that's 230 calories for Reese's Peanut Butter Cups in a 2-pack. In a 4-pack, which is what I usually indulge myself in, it's about 400. So why am I telling you this? The reason why is because yesterday we talked about energy. We talked specifically about energy being in units of joules, but this is actually another unit of energy, calories. So today we're going to be talking about a calorimeter, which is a device that looks at the energy released or absorbed from a reaction, and then we'll go from there. But before we do that, let's talk a little bit about what we spoke about yesterday, potential versus kinetic energy. Kinetic energy is the energy of motion. Remember, I'm walking down the street. I'm using my kinetic energy. Potential energy is stored energy, so it's not the energy of motion. And remember, kinetic energy is measured using temperature. So again, temperature is defined as the average kinetic energy. When heat is released, exothermic reaction is occurring, and when heat is absorbed, an endothermic reaction is occurring. All I really want you to do in terms of your notes is I just want you to copy down the Celsius and the Kelvin scale. You don't need to copy the Fahrenheit scale. Basically, I just wanted to show you that you've got your Celsius and Kelvin, which are the two scales we commonly use in science as well as in chemistry. And you might notice that I underlined absolute zero. Now, why did I do that? The reason why is because absolute zero is the spot in which all particles stop moving. Now, we've gotten very, very, very close to absolute zero. We never got to absolute zero as of yet, but we've gotten very close to it. So, by the way, one more thing I want to talk about before I move on to my calorimeter. To get your Kelvin value, you're going to take your Celsius. You're going to add 273. And that's equal to your Kelvin. So you might be thinking, Miss Wiswell, oh no, how am I supposed to remember this formula? 273 is such a random number. Don't worry. If you go to table T of your reference table, which I am going to pull up right now, as the last formula on table T, the last thing on the reference table, it gives you your temperature formula as Kelvin is equal to Celsius plus 273. So now you know you don't need to remember this. It's on table T, as in, thank goodness I don't need to remember this. Now the calorimeter. So this is called the coffee cup calorimeter. By the way, the only thing I want you to copy is this top bullet point right here. You don't need to draw the graph. So this is called the coffee cup calorimeter. Basically, it's called that because it's made of two coffee cups. You got your first coffee cup, which is right here, and then you got your second coffee cup. This one is just a beaker in this case that is surrounding it. So what is happening is inside the styrofoam cup is what's reacting, and in the beaker you have your water. So what happens is we're going to watch this reaction occur. We're going to take our temperature of our water before the reaction starts, and then we're going to watch the temperature rise until it stops. And then we're going to record that temperature as our temperature at the end of the reaction. That could help us figure out the amount of energy in something. So you don't need to draw this, but this is a more complicated calorimeter. So let's say I'm looking at the calories for a Cheeto. So if I were doing that, I'd put my little Cheeto right here in this reaction bowl. Or reacting cups. So what would happen is I would take the temperature of the water before, sorry about that folks, and then I would turn my ignition wires on, and that would cause them to raise in temperature. and cause my Cheeto to catch on fire. As a result, the steel bomb is going to become hotter, causing the water surrounding it to become hotter. We have a stirrer right here, which is going to be used to make sure the temperature is evenly distributed in our calorimeter. And finally, our thermometer right here, we're going to watch the temperature rise until we figure out what the highest temperature of this reaction was. And then we are going to take into consideration the mass of the Cheeto, and that kind of helps us to determine how many calories are in that single Cheeto. And estimating how many Cheetos are in a package on average will help us determine the amount of calories for an entire package. So, substances store energy in their chemical bonds. Specifically, when a bond is made, energy is released. When a bond is broken, energy is absorbed. More on that in a little bit. But the heat energy that is released by a substance should theoretically be equal to a chemical energy stored in the chemical bonds of that substance. What I really want you to focus on is what's bolded. The calorimeter indirectly determines the amount of heat energy stored by a substance by measuring the change in temperature for a known quantity of water which immerses that substance. So what are some common uses for a calorimeter? So common uses include, but are not limited to, finding the amount of calories in certain foods, specifically your dry foods. There's a different process for figuring out the calories in your wet foods, such as like soda or like pudding or something like that. So there's a different process for that. And finding the amount of heat released or absorbed from any kind of reaction, which is what we would commonly be doing in lab when setting up our calorimeter. So this is really the last thing I want to go over. We're going to be going over an example problem tomorrow, and we'll be doing some practice problems till you guys feel strong with this. So to determine the heat transferred or the heat gained and lost, or the amount of energy gained or lost, we use this particular formula, and the formula involves Q, which stands for the heat gained or loss, or the energy in joules. You've got your mass, which is in grams. You have your specific heat capacity, which is joules over grams, degrees Celsius, or Kelvin. And you have your change in temperature. Note, the specific heat capacity just indicates at which substance absorb or release heat energy. It's a constant value for any given substance. So again, for water, it's 4.2 joules per gram degrees Celsius. And on the reference table, it is Q equals MC delta T. Now, something you might notice if you look at table T and table B, which is where all this information is found, you might notice, first of all, table T is in the back, table B is in the front. They did that on purpose, so you could just flip-flop to find your information. But as you can see, you have your first heat formula right here. You have everything it stands for right over, I'm so sorry, my assistive touch is misbehaving, right here. And if you go to the first page of the reference table, you see we have table B right over here, but you might notice it's still 4.2 joules per gram Kelvin. It's still the same value. So you do not need to worry about the conversions as much in this case, because it is still that same value. And again, as always, thank you for listening. What I'd like you to do at this point is I would like for you guys to go on to the exit ticket. The exit ticket is asking today, what is the use, or what is the purpose of a calorimeter? What is it used for? Do not write that it's used for finding the calories of food. That is not what I'm looking for. I'm looking for the information I told you about today. So you're going to do that, and as always, thank you for listening, and I hope you guys have a wonderful, wonderful day.